If model upgrades feel like a coin flip, you need shadow traffic. We will mirror real requests to a candidate model, log both outputs, and compare quality before you flip the switch. You see flaky model upgrades at work. Sometimes the new model is better. Sometimes it regresses in small, silent ways that break production. Today you will learn how to run a deterministic baseline, mirror live requests to a candidate model, record paired outputs, and score their agreement. That gives you evidence to promote safely. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Upgrades are risky because users touch many paths you might not test. Shadow deployment gives you a quiet way to watch a candidate in real conditions without exposing users. Success looks like measurable agreement and a clear rollout decision, instead of guessing. This method fits between A/B testing and full rollout. It is light to run on small samples and scales to larger traffic when you add efficient routing. Conceptually, shadowing is simple. You send the same request to both the running model and the candidate model. You store both outputs side by side. Then, you compare them with a stable metric. If the candidate behaves similarly on typical traffic, you can increase exposure. If it diverges in risky ways, you hold back. We will follow one consistent toy example. The primary model will be a safe, predictable baseline that truncates text. The candidate will be deterministic, but different so we can measure disagreement. We will log one paired request, compute a simple token overlap score, show deterministic sampling for shadowing, and apply a small safety gate that looks at output length parity. This keeps the build clear and the decisions explainable. Now we prepare the baseline and a sample prompt. This snippet defines a deterministic baseline model and returns a primary reply. The list prompts holds two short inputs to simulate live traffic. The function MA lowercases the query, extracts alphabetic tokens with a regular expression, and returns the first 4 words as a concise response. That simple truncation mimics a safe, predictable baseline, so changes later are easy to compare against. We then compute out for the first prompt and print it for visibility. The printed primary response shows the baseline behavior that future steps will shadow and evaluate. The key idea here is to keep the primary output simple and totally deterministic, so any differences later are due to the candidate behavior and not random variation. Next, we will send the same request to the candidate and log the pair. This snippet fans out traffic to a shadow model and logs both outputs. The list pairs is our in-memory store of tuple records for later analysis. The function MB represents the candidate model by reversing token order, ensuring a deterministic but different behavior from the baseline. We produce a baseline answer A and a shadow answer B for the second prompt. Then we append an entry containing a synthetic request ID, the primary output, and the shadow output. The printed count confirms that shadow logging captured one paired result for comparison. The takeaway is that logging paired records gives you the raw material for offline analysis and lets you compare behavior on exactly the same input stream. Now we will compare the two outputs with a simple agreement metric. This snippet computes a similarity score to compare primary versus shadow outputs. We convert the primary text and the shadow text from the first logged pair into token sets. Using set intersection and union, we calculate Jaccard similarity, which is the overlap divided by the combined unique tokens. This gives a stable, scale-free measure of agreement between models without needing labels. We format the result to 2 decimals for concise reporting. The printed mean similarity shows how closely the shadow aligns with the baseline so far. Jaccard is forgiving to small reorderings and robust on short responses, which fits this toy example. Next up, we choose which requests actually get shadowed so we can control risk and cost. This snippet samples which requests get shadowed using a fixed random seed. We seed the generator to make routing decisions reproducible for audits and reruns. The variable rate is the shadow sampling probability, and we tally how many prompts would be mirrored to the candidate model. In production, you would use this decision to decide whether to invoke the shadow path per request. Increasing rate sends more traffic to the shadow and speeds evaluation, while decreasing it reduces cost and risk. The printed count shows the deterministic number of requests chosen for shadowing. Deterministic sampling helps you reproduce results for postmortems and tuning. Finally, we apply a simple safety gate that catches truncated or wildly short candidate replies. This snippet gates rollout using a simple length retention safety check. We set thra as the minimum ratio of shadow to primary token count to avoid overly short or truncated outputs. The lists A and B are tokens from the primary and shadow responses for the logged request. The variable keep measures how much content the shadow preserves, and DEC converts that into a clear go or hold decision. Raising thir demands closer parity and reduces risk, while lowering thir permits more aggressive rollout. The printed decision summarizes whether the candidate is safe to promote. This kind of heuristic is not perfect, but it catches a common class of regressions quickly. To map this toy build to production, replace the in-memory list with durable logs. Route per request based on the sampling decision. Compute similarity across a sliding window of traffic, and record decisions with request IDs for audits. Add lightweight timing measurements and cost accounting so you can correlate quality with latency and expense. Recap: shadow deployment mirrors live requests to a candidate while keeping users on the primary model. Use it when you need real traffic validation before promotion, especially for large or subtle behavior changes. Caveat: simple metrics like token overlap miss semantic regressions, so pair this with targeted human review on edge cases. Next step: scale this exact pipeline by logging thousands of paired records. Build an ANN index for embeddings to cluster disagreement cases, and run accuracy and timing checks across the clusters. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.